So customary sentences. Am I audible? And the screen is visible?
Yes, sir.
Yes, sir.
Very good. So this is the fourth unit, I mean the final unit which we are going to start today. And actually this theory, part of it is what you have already done. This is group theory. I'm not sure if all of you have done that. So all of you had the course on group theory or few? Or somebody who did not have?
So we had this course.
Right. Anybody who did not have this course?
So we don't have.
You did
So
not
we
have,
didn't
huh?
have.
You are from Delhi University or from some other?
No, sir. From
Sir, in DU also it's provided as a DSC, I think.
Oh, this is a DSC, not
Yes,
the,
sir.
this is not the core paper?
No, sir. It is
No, sir,
not a
it's
core.
not a part of core.
Oh, okay, chaliye, karte hain. But actually this unit is supposed to be big, 15 lectures, but we are not left with 15 lectures. In fact, I was just counting, including today's lecture, I mean, the one which you are having now, and the additional classes, we will have exactly 11 lectures remaining. So we will cover only up to that. We won't cover more than that. So we'll start with group theory, we'll go to representation theory, and idea is to understand things and we should be able to apply it. So from where it is starting? It is starting from this word symmetry. Now we know that if there are certain symmetry in the system, then those symmetries can be utilized in a very elegant manner. For example, we know that space everywhere is homogeneous. So if we are going to conduct a law, an experiment, let's say bar pendulum experiment, if to determine acceleration due to gravity. So taking care of the altitude effect, taking care of the friction, this result of your acceleration due to gravity remains same at every point. So one is of course that acceleration due to gravity is a constant, but it is also true for other experiments. If you are performing it here in India or you are performing here in US, you will get similar results. So what does that mean? This means that somehow the laws of physics are such that they seem to be invariant of the translation. So whether you translation in space. तो अगर आप यहाँ पे ये conduct कर रहे हैं experiment या कहीं और या थोड़ी दूर different colleges में conduct कर रहे हैं, you are going to get the similar results. Now translation invariance in space, जब हम ये कहते हैं कि there is a symmetry such that our laws remain same at all points in space, this leads to very important consequence. Does anybody know the consequence that laws of physics remain same at different positions? Invariance under translation in space. Okay. Euler-Lagrange equations. Whenever there is an invariance under some quantity, what happens because of that?
So conservation of some quantity takes
Conservation
place.
of.
Right. So this leads to conservation of some physical quantity. So space translation invariance that leads to the conservation of linear momentum. Similarly, if we say that the space is isotropic, that the laws remain valid at all angles, then this results in the invariance under rotation. So whether you are at theta 1 or at theta 2, you are getting the similar results, which results in the conservation of
Angular
Angular
momentum.
momentum.
angular
Angular
momentum.
momentum.
angular momentum.
Homogeneity of time, invariance under translation in time, conservation of
Conservation. Energy.
And
energy.
time translation.
Right. So comes a very important theorem. I am pretty sure that you must have Noether's theorem. Does somebody remember that? So this is basically the starting point of our discussion on group theory, that let's say if, so let me just write down, if Euler Lagrange equations, which is nothing but the equation of motion, they are invariant under coordinate transformation. So be it translation, be it something else, transformation. Then there exists a conserved quantity, which implies that symmetry plays a very important role in determining certain properties of physical system. And that's what the starting point, that we are talking about, that there exists certain symmetry in the system, because of which, let's say, the equation of motion or some remains invariant, then this leads to conserved quantity. So if we somehow know the symmetries, then we already know what kind of things we are expecting in the system. In fact, that is one of the good thing about the Lagrangian approach, that you are able to guess your conserved quantities once you understand the invariance under certain coordinate transformation. So group theory is basically nothing but the understanding that there exist algebraic structures which can explore the symmetry of the system. And consequently, that means that we will be able to understand certain conserved quantities of the system. We will be able to understand the system in a better way just by understanding the symmetry of the system. So that's the idea. With that, we come up with basically some sort of algebraic structure. All of you kindly mute. So that's the idea. Now we already talked about one algebraic structure when we started our unit 1. That was the structure which we called what? Linear vector space. Yeah. And this was when we were discussing about the superposition principle in quantum mechanics. Similarly, when we discuss about symmetry, independent of whether we are talking about quantum mechanics, classical mechanics, or any system, then we talk about something what is represented by these two, which we call as a group. So a group which will be an algebraic structure will be useful for understanding the symmetries of the system. So when we are saying that symmetries of the system, that's a very qualitative word. Quantitatively, we say it in terms of this algebraic structure, that we know that there exist certain operations under which our system will remain invariant. And that's the starting point, that there exists something what we call as a group. So a set, let me just start with a definition. A set of elements, let's say G1, G2, so on and so forth, along with a binary operation. So binary operation, in my notation it is right this. So this is the binary operation and this is a set. This is called a group if it satisfies the following 4 axioms. So it is something very similar to what we did in our linear vector space, that we defined linear vector space to be a set of vectors along with 2 operations. One was the vector addition or some sort of binary operation between the vectors, and another was the scalar multiplication. Here we are talking about only the group of elements and a binary operation if it satisfies the following 4 axioms. How many axioms were satisfied in the case of linear vector space?
10.
So 9.
Yeah, I mean, I put it in terms of 10 exactly. I mean, if you go back in my lectures, but it is up to us. How do we define it? So this 5 is not needed here. How many of those 9 or 10 were for vector addition?
So 5.
5?
5.
Four actually.
Okay, we will talk about it soon. So let's say G1, G2, G3, these are the elements which belongs to set G. Then the first of the axiom is a closure. What would be closure? That if G1 belongs to G, capital G, and G2 belongs to capital G, then the binary operation of G1 into G2, that will also belong to this group. So that's a closure. Then identity. What is the identity? It's very similar to what you did in your linear vector spaces. What would be identity? That there exists an element which I will call as E, which when I am going to multiply with, let's say, G1, then this will leave the group element just as it is. And this identity element is a unique element. Then there exists inverse. Can somebody guess what would be the inverse? That if there is G1, then there must exist
minus G1.
G1 inverse. Okay, I mean it is just about how we are going to write it. So there exists another element mandatorily, that there exists this element G1 inverse, which will give the result
Identity.
Identity.
Very good.
Identity.
And this inverse is also unique. Similar properties we were seeing in the case of vector addition and associative. So G1, G2, G3, ordering of the operation is not important. Whether you do G1, G2 first and then do the composition or binary operation with G3, or whether you have the binary operation of G2 and G3 first and then have this. So if these four axioms are satisfied for any set of elements Gi's, then we call that set along with the binary operation a group. Remember, both G and the binary operation are important. Even though it's customary, you will see in the text to write just G as the group. But whenever a group comes, please try to see that there exists two things. One is the set of elements and another is the binary operation. As the word binary says, that it will be an operation having two of those elements. So binary, right? So that is what the binary operation is doing. So we'll come to examples soon, but first thing first, that this group structure looks very close to the linear vector space, this structure. So if I forgot about scalar multiplication and I just talk about this, it looks like that we are very close to that, except for one thing. So what is one thing which is missing here, which was there in the linear vector space?
Commutativity.
Commutative.
Right, that there does not exist any commutative nature or a structure. So G1 star G2 may or may not be same as G2 star G1. I'll come to that. But one, that this algebraic structure looks very similar to partial structure of the linear vector space Vn plus without the commutative rule. That's one that we'll have to always remember. This structure in itself is sufficient to explain many beautiful things in physics, and as I have mentioned, it's the symmetry which we are going to exploit now this time. Last time we were explicitly trying to figure out that how to write down the calculations with the wave functions, what are wave functions, things like that. Here we are not worried about the quantum mechanics only. Whenever there exists any symmetry, we will try to write down that in terms of certain elements, and those elements when applied on a system should give us something, should tell us something about the system. So I'll let you ask questions at this point. So in principle, you may ask me that, sir, you should have done group theory as the first thing and then you should have come to linear vector space. And in some sense, you are not even wrong. It is just that the group theory, after becoming the group theory, goes to something what we call as the representation theory, where we will be utilizing our knowledge of linear vector spaces. I will have to make the disjoint set of group theory. Otherwise, I would have started with group theory, I would have done linear vector spaces, and then I would have come back on representation theory. So instead of doing that, I just took linear vector space. I will do group theory and I will come to linear representation theory very soon. Yeah. So that's the reason why I just wanted to do it in a single go. Okay, so one thing which is pretty obvious and which will actually be interesting, that there exist certain groups, now that the group definition is defined, that there exist certain groups which are called abelian groups which enjoys this. What is this?
Commutative.
Commutative.
Right.
Commutativity.
So commutative operation. Right. So those groups which additionally have this commutative structure also defined will be called abelian groups. Abelian groups will that means it's a group having this additional one. For very important thing, for all pair of elements. Now, why this is very important? You go back to previous one, look into this E and inverse. Both of these elements, so there has to be a unique identity element. If you look into that, or if you look at the inverse, both of these guys are commutative. That means inverses are all commutative in the group. Identity, which is a unique element, single element, that's also commutative. But it may not be generally true for other elements. Even if it is not true for single element, then also we cannot call that group an abelian group. So what is the interesting thing about the abelian group? All pair of elements belonging to G, all pair of elements, they will follow this rule, which is what we call as the commutative rule. So those groups which do not, non-abelian, the one which in general may not follow it, but that does not mean that for one pair or for two pairs it will not have. It is just that for all pair it will not have this commutative rule. Yeah. So first categorization of the group becomes very apparent since we know about our linear vector space. And this also tells me, that means that in general, if we talk about a group, and I do not talk about abelian group, then ordering of operation becomes very important. What do I say here? So what is this property G1 star G2 is equal to G2 star G1? The property says that whether you apply first G2 and then apply G1, or whether you apply G1 first and then apply G2, then they remain same. So if you have a system on which you are applying some transformation G2 first and then G1, this will be different from saying that first G1 is applied and then G2 is applied. It is on in selected groups which are called abelian groups where the order of operation does not matter. So by the definition of the group, which does not include commutativity, there the ordering of the operation becomes important. Questions up to this point? Definition of the group or the abelian nature of the group?
So we can't divide any group into abelian and non-abelian because they are separate.
No, I mean, if there is a possibility, if there exists a possibility, we will come up with subgroups, right? And when we'll discuss subgroups, there, if the okay, I mean, if there exists this option, then there may be operation. It is not true that in general you can always divide group into abelian subgroup and non-abelian subgroup. It's not true in general.
Okay, sir.
Good question. Anybody
What
else?
if this group is empty?
Can that be empty? That's a very good question. Can a group be empty? Go back, previous page. By the definition,
At least identity should be there.
But what about the inverse of the identity?
It can be the identity itself.
Very nice. That means that there has to have at least one element. It has to be a non-empty set. It has to be. Linear vector space, the same point was there. It has to be a non-empty. So the existence of identity tells you that group will have, the set will have at least one element. Although, I mean, you won't do much with that element, but okay, I mean, technically your question is valid that a non-empty set cannot be a group. So let me write somewhere. The set cannot be a group. Good question. Anybody else? Identity. Okay, that's the easiest thing to understand any algebraic structure is to understand the examples. So let's just take few examples, try to understand that, and then I think we will be in a better position to understand it further. So I always start with group of numbers. So Z is common way of writing for me an integer, but can I
Sir?
just write Z and ask you whether it's a group or not?
तो empty नहीं आएगा.
Cannot be a group.
Yes, sir,
Non-empty
it should
set
be
cannot
empty.
Empty set cannot
Sir,
be a
जो
group.
लिखा है
वो तो
आपने वो
ओ
वो वही
आपने जो बोला वो मैंने लिखा नहीं है, मैंने उसे okay, a group has to be non-empty. Yeah, this is what you want me to write, right?
Yes.
Yeah, thank you, thank you. Okay, I said something and I wrote something else. That can be the worst thing which a teacher can do. Thank you for reminding me and correcting me. Yeah, okay, examples. Z, integer. Can I ask you whether integers is a group? Can I even ask this question?
Sir, under
So we
which
need the
operation?
operation.
I need binary operation, right? So let me say Z under this. Is this a group? What is this group? Set of integers with ordinary addition of integers as the binary operation. Is this a group?
Yes, sir.
Yes, sir.
Yes, sir.
So closure is there, integers addition. Integers addition
Yes,
is
sir.
an integer. Yes, okay.
Yes, sir.
What about the identity? It will be
Zero.
zero is the identity element. What about the additive inverse?
The negative of the element.
Minus of that.
Minus. Minus, okay. What about the associativeness? Okay, I do not know to worry about associativity. So what about this? Z and ordinary multiplication. So yes. Group.
So it's not a
What
group.
about this?
No, sir.
No, sir. Why it is not a group?
Sir, the
So
inverse,
closure
sorry,
property-
inverse won't
So
exist.
inverse
Or
of
zero.
5.
Inverse
Let's say-
identity.
Okay,
Or
inverse
zero.
of 5. What is that? 1 over 5.
Yeah, it won't exist.
So this guy won't exist because 1 over 5 is not an integer. Yeah, sure. And somebody said identity should exist, right? I mean, 5 into 1 is equal to 1 into 5 is equal to 5. Identity is there, right? 1 is an identity element. That's not a problem. Multiplicative identity, that's not an issue. It's the inverse or something else, huh? Inverse of 5. So let's just see. What about this? Where R is my group of real numbers. So I expand. Instead of Z integers,
Yes, sir.
real
No,
numbers.
sir.
It is a
Sir, it's a
No,
group.
sir.
Sir, not a
Why
group.
it is not a group?
So
sir.
zero ka inverse doesn't exist.
Zero.
So there exists an element 0 if I ask what is the inverse of that. For inverse, you need to first know what is the identity of this group. Identity is 1. So E
One.
is 1. That is the multiplicative identity. Such that if I multiply any real number 5.0 into 1, this is 1 into 5.0 is equal to 5.0, right? So that is our identity element. Now talk about this 0 as an element. If you want to get 1, then you will have to think about multiplying it by 1 over 0. But 1 over 0 is infinity, it does not belong to. So inverse of 0 does not exist. Yeah, that means even R cross is not a group. What is group is generally written as this guy R, okay, real number minus this. Very nice. Yeah, I do not know this song. Okay, but this guy R star ordinary, this guy will be a group. So removing 0, single element 0 from the real numbers, that will under the multiplication will be group. Although under addition, this guy will not be a group. Yeah. So you will have to keep on thinking about only 4 axioms. Okay. What about this C, complex, under complex multiplication? Will this be a group? Shouldn't take that much of the time.
Yes, sir.
But shouldn't take that much
Yes.
of the time. Complex multiplication will have the same problem which this guy has. 1 over 0 plus I0. Yeah. So this guy
Yes, sir.
also have
It
the
is.
same problem of the inverse. So this guy won't be a group. What will be group here also?
C
Non-zero.
Minus zero.
zero.
All
Zero.
Right. So C star, which you will have to define 0 plus I0 or the set of two real numbers, and that will be again a group. So, okay, this is something which you can keep on doing with the rational numbers, figure out whether they are or not, under addition, under multiplication. Anything under subtraction or division can be a group or not. Think about it, anything. So, before matrices. So, first was set of number, now matrices. So, let's say I take n cross p matrix, real complex, I do not care at this point of time, and matrix addition. So this is matrix addition. That is why I always say that write two things to begin with. Is this a group?
Yes, sir.
Yes, sir. This will be a group. What about m n cross p under matrix multiplication?
No, sir.
Will this be a group?
No,
Why
sir.
it will not be a group?
Some
Yes, sir.
multiplication property will violate.
So there won't be any
Associative
multiplication. So a
Sir,
n
it
cross
should.
p into b n cross p, you can't even multiply because these two guys are not same. This guy cannot be. Okay, let's just continue, figure out. M n cross n under matrix multiplication.
It can be, sir. It is actually. It is.
Yes, no.
Sir, it is.
Yes, sir.
Okay, give me identity element of M2 by 2.
1001.
Identity, this will be 1001, right? Now, just a general one, A, B, C, D. Yeah. What will be the inverse of this guy? A.
minus A minus B minus C.
So under matrix multiplication?
So it will be 1 upon AD minus BC.
Yes, yes.
No, so you should write A inverse, which is A inverse A, that is equal to identity, right?
Yes, sir.
But
Yes,
then
sir.
A inverse, for A inverse to exist, what should happen?
Sir, the matrix should not be singular.
That means that M n cross n under matrix multiplication, will this be a group or not?
No, sir. Until the matrix is not it's not singular.
Non-singular or invertible, right? So please see that M n cross n in general under matrix multiplication is not 1. However, there exists now at this point of time, I will write down something in an interesting way and I will just mention what I have written. So let's consider a group of matrices A, B, C, D, where each of these element A, B, C, D is a real number such that AD minus BC is not equal to 0. Remember, this is the determinant of this 2 by 2 matrix. So nothing but determinant should not be equal to 0. And this is what is called for the matrices general linear group G under matrix multiplication. This R, that all elements are real. 2, we are talking about 2 by 2 matrix. This guy is a group. The group of matrices in which the determinant is not equal to 0. So the invertibility condition is true if the determinant is not equal to 0 for any square matrix. But this leads to a general GN. What will be this group? Can anybody say that now?
So n cross n matrix with all non-singular matrices.
N cross n matrix, N cross n real elements. Yeah,
Yes.
this is the real one with the condition that determinant of all the matrices, they are not equal to 0. That will be group. In fact, I can even take it into the complex plane. So this will be n cross n complex matrices with determinant not equal to 0 under matrix multiplication. They form group. Multiplication. This forms group. So this guy forms group. So matrices, they interesting one. What about the unitary matrices? Unitary matrices. So what is unitary matrices? U dagger
dagger
is
U.
equal to U inverse, or U dagger equal to U dagger, U is equal to I. So now
Identity.
set of unitary matrices U n cross n. Will this form a group under matrix multiplication?
Yes, sir.
So
Do you
no.
know that? So you know the determinant of unitary matrices?
1. Modulus is always 1.
So if you know modulus of determinant U is equal to 1, which is surely not equal to 0, we already know that the inverses exist. That is what the unitary matrices are by default. So will the unitary matrices under this? So the only question to answer now, U1, U2, will this belong to the group or not? Multiplication of two unitary matrices. Is it a unitary matrix?
No.
No, sir.
So it's not
So
necessary.
this is a homework for you guys. Please
Yes.
figure out that. It's a very important one. And we did it. I mean, when we were doing the general operators, we were doing that. The product of unitary operators, whether that's a unitary operator.
Yes, sir.
So
It
then,
is unitary operator.
so that means that there is something which is not letting you give the reasonable answer. So let's just take it as a homework and you will tell me in my additional class. This is, in fact, this guy makes a very important group. We will discuss it in the continuous groups, but this is a very important one. In fact, I can actually do the same thing for orthogonal matrix. What is the difference between unitary versus orthogonal matrices? These guys have what kind of entries?
So real entries.
In the unitary, it was complex, and in orthogonal, it is nothing but the real version of that, right? I mean, this is what we did. So how do we define that? OT is equal to OT, right? Or OOT is equal to 1, 1 means that.
सर एक्स्ट्रा साउंड आ रही है.
जी मेरे से तो नहीं आ रहा है, किसी ने ऑन किया हुआ है, आप क्या कर सकते हैं? I also was facing the same thing. Please mute when we are not answering. Okay, so at this point of time for the matrices, I will let you think about unitary matrices and orthogonal matrices. They are basically real and the complex counterparts, and they both form very interesting set of rules. But for you, only one thing is to be checked, that those four axioms, whether they agree or whether they do not agree. If one of the axiom is failing, then that means it cannot be a group. Okay, so let's just move to something else. Set of complex nth roots of unity. Nth roots of unity. So Zn is equal to 1 and of course greater than equal to 1. I just start with, let's say, even Z is equal to 1 is interesting, but let's start with Z square is equal to 1. So does somebody know what would be the solution of this guy?
Plus minus 1.
Okay, so let's consider a set which has two entries, 1 minus 1 under, although it doesn't matter whether I do complex or real multiplication, under complex multiplication, since I'm doing the complex and as root of a unity, and hence I will write generally complex multiplication, which in this case will be just the real multiplication. Will this form a group? Remember, without binary operation, I cannot define my group. Now I define binary operation to be just a product. Will this form a group? Will there be all the four properties verified? What is first property? Closure. So what are the possibilities?
Yes, sir.
1
1
into
cross
minus 1 and
1,
1 into 1.
1 cross minus 1,
So-
minus
so-
1 cross 1, minus 1 cross minus 1. Are all these guys there in your group in this set?
Yes, sir. They
Yes, sir.
Yeah.
Yes,
So
sir.
first property satisfied, which is closure. Second property, identity. Under multiplication, what will be that? Which
Yes,
will
sir.
result in
Sir, 1.
Sir, 1.
1. What about the inverse? What will be the inverse of 1?
Sir, 1.
It's in
What is the inverse of minus 1?
minus 1.
So minus 1 is its own inverse. Identity element, okay, identity element is always equal to inverse as well. So that means the inverses also exist. Associative nature, I do not need to worry about 1 into minus 1 into 1, whether it is equal to at what ordering I will apply it. Does it matter?
No.
No.
No, sir.
So
No, sir, it
that means that set of complex, at least square root, is squared. That is 1 minus 1, a set of these two numbers under multiplication forms a group. Now, although it will be intuitive to do z cube is equal to 1 also, but I will first do z4 equal to 1, and this I will give you as a homework. I will pick it up later soon. But what about z4 is equal to 1? Can somebody tell me this set?
Sir, 1 minus 1
1 minus 1
omega
I-
square.
Sir, iota and minus iota.
iota minus iota. How did
Yes.
you get that, by the way? EI 2 pi over 4, then EI, then 4 pi by 4. How did you get these numbers? I just wanted to ask.
By solving the roots, the equation we
Sir, like this
solved
only.
in complex.
E pi.
But you must have written it, right? I mean, this is the simplest way you do that. So I'm just thinking, I mean, what did you do? Okay, I mean, we did not do it, and you should be able to write it because z cube will have that coming in surely. But you should be able to write it in exponential, and that is why I said
4 pi by
under
4, E
complex
pi I, 6
multiplication.
pi by 4.
6 pi, so 4
6
pi by 4.
Yeah, then 6 pi by 4 and then 8 pi by 4.
So 8 pi by 4 is just 1, right?
1.
Yeah. And these guys should give you ei pi by 2 and ei pi, then ei 3 pi by 2 and this. Right. This is what I was just hoping. And this is the same thing which you can do here also. But under complex multiplication, let's just come to think about this guy. Will this form a group? So please check few properties at least to make it clear to you. Please check it.
Yes, sir, it will.
Okay,
Yes, sir.
so Yeah, I mean, this can be pretty quickly checked. 1 into -1 -1, 1 into I, 1 into -I. Okay, that is done. -1 into I. Okay, these guys will remain within that cell. So the closure will be taken care of. Then you can, of course, what will be the identity
Sir,
out of 4?
Sir,
Yes.
Sir, 1.
Right.
can we do that table thing that we used to do in our
But
graduation?
at this, see, the point is, several of you have said that we did not know what is group at this point of time. I do not want to invoke it. I will bring it exactly at the time when I want to. I will bring it. Don't worry.
All right, all right.
Yeah. Kelly multiplication table is what you are talking about. We are going to bring it. Yeah, right now it is just checking the 4 properties. Yeah. So I won't go for higher groups than this right now. So set of 2 into 2 rotation matrices, r theta, cos theta, sin theta, minus sin theta, cos theta, under what? 2 by 2 rotation matrices. That means under what kind of operation?
Multiplication. Matrix.
Again, matrix multiplication, right? So what will be this kind of multiplication we are going to talk about? We are going to talk about, for example, if you have to check this closure, then you have to think about 2 matrices, r theta 1 into r theta 2. Will this result in a matrix which looks similar to this guy? If yes, then the closure will be taken care of. Yeah, otherwise not. Then we'll of course have to think about identity inverse, but those things will come rather naturally. This guy will also form a interesting group because here we are talking about the rotation matrices. So we can now think about what? We can think about a 2-dimensional plane. We can apply our rotation operation on certain vectors, which results in something. So if a system remains invariant under that, what could be the consequence? So we are moving in that direction, and group has this interesting thing that I do not need to just think about the numbers, etc. But the interesting thing will come up from this one, the one which I am doing now, which I will call as the shapes, or in general dihedral group. So let me just say what it is. Yeah. So let's take an equilateral triangle. Yeah. So let's just take that. And let me just put, just for our sake, I mean, equilateral triangle is equilateral triangle. Just for our sake, I just put A, B, and C at these 3 places for identifying only the vertices. What are the operations which will leave equilateral triangle invariant? So now I am interested in understanding operations. So which will leave equilateral triangle invariant. Invariant means that whatever you are seeing right now, the equilateral triangle will come back. Forget about these ABCs. This is for my reference only. The triangle will come back to its original shape. So what operations you can think of?
Sir, rotation by
Rotation.
So if I, let's say that there exists a rotation about the plane, I mean, this is the 2-dimensional plane. So I have an axis which is perpendicular to this. And if I am going to make a rotation about what? Rotation by what? So let me just do. If I do not rotate, rotation by 0. Or I mean, some people call it by 360-degree, what will happen? I call this as first operation.
So it remains as it is.
It remains this with my A, B, and C at the same place. Okay. So this is this guy leaving it. Any other rotation?
Sir, by 120 degrees.
So rotation by 120-degree, or I call that as, can I call it 2 pi by 3? What will this guy do? What will happen to my ABC?
Sir, A will now go in place of B.
Okay, and that
And B
means
in
B
place of
here
C.
and C. So look at the triangle, whether the triangle remains same as the original one.
Sir, the shape is same. Like,
Yeah, shape is what I am looking for. ABC is only for my reference. Others, please.
The
Yeah,
shape
remains
will
same.
be
Yeah, I mean, if you
shape
talk
will
about a
always be same, I guess.
always, if you rotate it by 90 degree, will the shape remain same? I mean, will this guy will look like this, or will this guy look like this?
Oh, okay, sir. Yes.
Yeah, I mean, what you are saying, the shape and the structure, the one with which I am starting with, right? Of course, okay. I mean, in case the shape, you are saying that deformation of the shape will not take place, but I won't take this as my symmetry because this won't be exactly like this. You see that my this particular axis is now rotated at 45 degree. Yeah, so I have to apply a rotation also. But I want my figure to be intact, just like it. So vertical, this guy and this guy and this guy. So by 120 degree, if you are doing it, is this intact or not?
Yes, sir.
Yes, sir. Any other rotation?
Sir, by 240 degree.
240 degrees.
Rotation by 240 degree in terms of pi, what should I write?
4 pi by
4
3.
4
by
pi
3.
by 3. Thank you. I call that as next one. What will happen to my inner indices, which I am just keeping track of?
So it will be the left corner A.
A.
Sir, A will go in place of C.
Okay.
B in
And
place
this.
of A.
Okay. Any other operation? If not rotation if you are exhausted.
So flipping it in 180.
Flipping it by 180 degree, or I will call it as
Mirror image.
reflection. Yeah, I will call it reflection number 1, for example. This kind of a reflection which I have drawn. What will this reflection will do? So reflection
B and C will change positions, like they'll swap.
about A. So I call this, okay, I have to give something, and this guy will make this exact same. So A remains at the same position, B and C will swap. Very good. Any other reflection? Reflection
So
Sir,
about
about the two medians which
remaining
are there.
points, sir.
B. So that is about B. I will call this L2, and this will make what? So B remains same, and A and C exchanged position, and then there exists about C, which is what we call, that means C remains same and A and B change position. So if you look into it, these are 6 operations together. So I will, let's just say it, R1, R2, R3 commas, of course, L1, L2, L3. These are 6 operations, out of which 3 are rotations and 3 are reflections. Will this form a group? So these are group of operations. Now, will this form a group?
Yes, sir.
Yeah, but there is a big question. Big question is what? Under what binary operation we are talking about? So this kind of binary operation which I will define. So remember, this is the question, this is the point which I started with. Just don't look at the elements itself. Also think about what is the binary operation. So binary operation is something like this. For example, I can think about this. R1, R2, where on the triangle I will first apply R2. So this will be my first, which is, oh God, this is the first operation I am going to do. So let's say rotation by 120 degree. It will leave the figure invariant, but it will result in C, A and B kind of inner indices. And after that, I apply R1, which is my 360 degree, and that means that it is going to just leave it at CAB. The figure of course remains same, but this is what I call as the binary operation, applying one rotation R2 first and then applying R1. I can talk about anything. R2 times L2. So I apply L2 first and then I apply R2. So these set of operations which leave equilateral triangle invariant under this thing, I mean, please remember that this is very important as the set of elements composition rule that forms a group. This is what we call as the dihedral group. Under common way of writing, since I am using just star for any general group, so I will use this R1 dot R2. At times you will see that in most of the places people do not even write this guy. So instead of writing R1 R2, it is written as R1 R2, which means that I am going to apply R2 and then I am going to apply R1 on the triangle. So please understand that it is still an operation which we are applying, a rotation by 120 degree first and then rotation by 0 degree. So all of these possible operations are there and they will remain closed. That means that the closure property will be there. You will find that there exists an identity element. Can you tell me what is the identity element for this one?
Sir, R1.
Right. R1 is the identity element that leaves the group just like that. You apply R1 on any of it, you will find out that the figure will remain whatever it was. So it's a common practice, for example, to write down this as E, this guy as rotation by 120 degree as R and rotation by 240 degree, which is as if I am applying my R twice. So R square, you will find out that the books write this structure also commonly for this group, where identity element is nothing but rotation by 0 or 360 degree. R2, which I said the rotation by 120 degree is the rotation R, and R3, which is 240 degree, is nothing but two operations. Now R square will be what? So R square will be R dot R. That will be my R square, which means I am applying first 120 degree on my triangle ABC, which was the original one, and then I am again applying 120 degree. And you will find out that we will reach this figure BCA. So this is where I will say that the group is going beyond just the simple quantitative structures, that I do not need to think about only the numbers, the matrices, the complex roots, but I can now start thinking about even the shapes. Crystallography, for example, the crystals, you are coming up with sort of so many groups now. You must have heard about that Kittel book starts with a group, etc. So why it is able to say about that? Because they form something what is more technical, which is called mathematical groups, nothing but the algebraic structure. I can go beyond that also. I can think about square. How many vertices do a square have?
4.
4 vertices. So I can now start thinking about the rotation and the reflection and any other possibility in case if you can think about those operations, and that will be something like going to D4 group. How many elements are there in this particular group D3 with this composition? 6. So you can even think about that the number of elements in a group here is 6. So if there is a square and I go for D4 composition, how many elements I might be thinking of?
8, sir.
8, sir.
2 into 4, 8. How many rotations, how many reflections?
4 each.
4 each. Right. So that is how one can think about. That is why this is a general dihedral group, which is at times you will say written as Dn under composition. I have considered a particular one, but I am going to use this group very often in my discussion because of course I will keep on applying the examples. So at this point of time, I will just stop here and let you ask question and absorb what I have done. And then I will move forward. So please see that group exploits symmetry of the system. It is something that we are going to utilize. And that's why this algebraic structure comes. Now, once the algebraic structure is there, it has to be defined. The algebraic structure group is defined in terms of a set or a non-empty set of elements along with a binary operation. Two things have to be there. Along with that, the 4 properties must be ensured. The closure, existence of unique identity, the existence of unique inverse, and the associative nature. While going through further, we said, that the groups can be of two kinds. So first categorization of the group, abelian or non-abelian, depending upon whether this property of commutativeness is there or not. If it is there, then we call those groups as abelian group. If it is not there, then we call those groups as non-abelian group. For a group to exist, this commutativity is not mandatory. But if a group has this commutativity for all pair of elements, then we call that abelian group. In general, if the commutativity is not there, that means that the ordering of operation becomes very important in a group. So a question which can be asked for the final group is whether that group is an abelian or not. We will discuss this question later on. We will reserve this question, but we will answer that. And then we came up with the examples. Our first examples, of course, came up with just the numbers, which is easiest to think about. Then we, of course, went into what we call as the matrices. All we have to check those four properties and nothing else. In principle, we are not checking anything else at this point of time. I asked this question, unitary matrices. Somebody did say at the end that U1, U2 will be a unitary, but please check that if you found out that or not, because that's a very important closure property. Yeah. So, okay, this will come out to be group. We have set of complex nth root of unity. We have come up with the rotation, set of rotation matrices, and we are coming up with now the shapes. So you can see the idea is that we are expanding the knowledge of this algebraic structure group and applying it in variety of things, starting from numbers, going to matrices, going to complex numbers under multiplication, then coming to rotation in two-dimensional plane. We will find out rotation in three-dimensional space as well, and then shapes of this dihedral groups. So groups are defined in such a manner that it can be applied to variety of places, not just to any limited set of places, and hence group theory plays important role in both classical as well as quantum structures. So that's very important to note. It's enjoying the property of symmetry, not anything related with quantum or classical. It can be applied anywhere. Two physicists who played pioneer role in applying group theory in physics, they were now you may or may not have heard the name of Wheel and Wigner, but in 1900s itself, 1920s onwards, this group theory starts becoming important because it played very important role in nuclear and particle physics. In fact, this guy Wigner, of course, you will read in your nuclear particle physics text, and Wheel, of course, those who are going to do more of the field theory, etc., but in the particle physics. This started becoming more and more prominent there, but does not mean that the group theory was not existing earlier. Mathematical structure group theory was there for so many years. In fact, the person who started with is still a very young mathematician. At the age of 21, he died. But this is sometime you will just read something written as Galois theory. So that structure was always there in mathematics. Physicists started using this structure, and these two guys both wrote book. Wheel wrote a book, Wigner wrote a book, and it is interesting that there is a very contrasting style of the books written by these two authors. Very contrasting style. Somebody who is interested will ask me what is meant by this contrasting style. Others may take a long route. They can actually read if they want to. Although I will tell you my reference is not in today's class, but maybe either in the additional class or day after tomorrow, when I'll have a little bit more of done. Most likely those guys who have done it in their BSc, they generally use this text, I guess, Galilean contemporary algebra, abstract algebra, or contemporary abstract algebra, right?
Yes, sir. Abstract algebra.
Algebra. This is what you might have used. This will only take partial care of our syllabus, and this is a heavy text. I mean, so many things are written because it just did not want to leave anything, left out. But then this is a very heavy text. Those who might be reading it, they will find that they will have to read lots and lots and lots and lots of pages actually for this one. It's a very good book, without doubt, but it is only catering to one aspect, which is called group theory, whereas we'll have to take group forward into what we call as the representation theory as well. So I will reserve my sentences about that. I have already reserved one particular question, whether the group which I have discussed just before this guy is an abelian group or not an abelian group. Does somebody want to make a guess here? I will answer this question later on. In fact, we will together answer this question.
No, sir.
Okay. So it's not an abelian group, right? Or you do not want to make an educated guess?
Sir, it is not a abelian group.
Okay, good. Thanks. I just think. Okay. Anything particular which you want to ask with what we have done? Because now I will use all my lectures, basically including the additional class, to flow with the lecture, and I will keep on taking examples just like I am taking the example here. This particular group, dihedral, will be my base one, but it does not mean that I am not going to talk about others. I will keep on talking about others as well. Questions?
Do we have the additional class today?
Yeah, sure. I mean, I cannot live without that now.
All right.
Yeah, I can in principle if I keep on giving you homework. I do not want to do that. It's just that. You understand, group theory is so abstract at times, and the name of the book is also saying that students keep on running away from group theory. I just don't want that to happen in the class.
So in our BSc we read R. Kumar, abstract algebra by R. Kumar.
मैंने कभी नहीं पढ़ी है, तो I cannot even comment on that. I will give you reference surely, but I haven't read this book. I haven't even known that such a text existed. I'm sorry, but it does happen sometimes. Yeah.
All right.
Okay.
So, R. Kumar writes other books also for differential equations. मतलब differential equation ज़्यादा popular है.
होंगी पर Arjun somehow okay. I missed it. Let me say like that.
Sir, what
Yes,
is symmetric about a group of integers?
Oh, symmetry. The symmetry is coming in the question itself. The binary operation is symmetric, right? You started with natural numbers. Remember जब आप लोगों ने पढ़ना शुरू किया, numbers आपने देखे पहली बार, आपने कहा कि natural numbers से शुरू करेंगे, zero भी आया नहीं था तब तक, whole number भी नहीं आए थे, तो आपने कहा 1 2 3, फिर धीरे धीरे आपने addition करना शुरू किया, 1 + 2 = 3, 1 + 3 = 4. If I ask you whether set of natural numbers form a group under addition, what will you say? उसमें कुछ सिमेट्री है जो कि ग्रुप थ्योरी एक्सप्लॉइट कर सकता है?
सर उसमें इनवर्स एग्जिस्ट नहीं करता.
अब आप समझो कि मुझे अगर नंबर्स को एक्सपेंड करने थे नेचुरल नंबर से, अगर मैं मैथमेटिशियन हूं, तो मेरे लिए कितना आसान है ये सोचना कि मुझे नंबर्स एक्सपेंड करने के लिए चाहिए क्या, राइट? अगर मैं ग्रुप थ्योरिस्ट एक मैथमेटिशियन हूं, मैथमेटिशियन थिंकिंग अबाउट ग्रुप, एंड आई एम लुकिंग एट नंबर्स, नेचुरल नंबर्स, आई एम अनएबल टू एक्चुअली फिगर आउट एनीथिंग इन टर्म्स ऑफ एडिशन, क्योंकि मुझे ये नहीं समझ में आ रहा है कि मैं उनको कैसे इनवर्स और इस तरह बनाऊं. तो मुझे नंबर्स एक्सपेंड करने कितने आसान हो गए, सोचो. All I need to think about, let's put something which will leave those natural numbers invariant. तो आपने जीरो ऐड कर दिया, होल नंबर बन गए आपके, राइट?
Yes, sir.
एंड देन आपको सोचना, अरे जीरो तो ऐड कर दिया, पर मेरा ये जीरो कैसे बनेगा, 1 में क्या मिलाऊं कि जीरो बन जाए? फिर 3 में क्या मिलाएंगे जीरो बन जाए? You will start thinking about, okay, negative number line you can extend to. So अगर आप सोचो कि if you look at it from the symmetry properties, then you can think about expanding this one. In fact, some of you might have heard about these numbers called quaternion. Some of you might have heard about quaternion. Have you? No.
Yes, sir.
Okay, some of you. So आपको अगर आप सोचोगे तो once people understood कि numbers में symmetry apply करी जा सकती है, and we can think about forming groups, then you can actually start expanding the numbers beyond real numbers. You went up to complex number. Can I further expand complex number to come up with certain set of numbers which can be very, very universal? So people can start thinking in that direction. अदरवाइज नंबर को एक्सपेंड करना इतना आसान नहीं है आपको सोचना. हर बार आपको ये प्रॉब्लम्स आएंगी, आप ये सोचोगे कि मैं नंबर इस केस में ऐसे यूज करूं, इस केस में वैसे. बट नंबर सिस्टम को, इफ यू जस्ट लुक एट द इवोल्यूशन ऑफ नंबर सिस्टम, you will find that group theory is giving a very beautiful basis for expanding the number system. Right? I mean, this is what the point is. In fact, आप लोगों को already पता है, मैं आपको बता देता हूँ, now that you have asked the question and I am eating up your time and my time as well. Rotation matrices. अगर मैं एक वेक्टर के ऊपर एक रोटेशन लगाता हूं और उससे क्या कोई चीज इनवेरिएंट रहती है? अगर कोई भी चीज इनवेरिएंट रहती है, सोचो, और रोटेशन ग्रुप बनाता है और उससे कोई एक क्वांटिटी भी इनवेरिएंट रह जाए, तो वो क्वांटिटी बड़ी इंटरेस्टिंग रोल प्ले करेगी कि मैं एक्सिस को कितना भी रोटेट करता जाऊंगा, वो क्वांटिटी इनवेरिएंट रहेगी. यानी कि मैं कई इनवेरिएंट क्वांटिटीज बनाने के लिए केवल ये सोच सकता हूं कि लेट मी कीप ऑन अप्लाइंग रोटेशन ऑन द वेक्टर्स एंड सी इफ सम क्वांटिटी आई कैन जस्ट स्टार्ट थिंकिंग अबाउट इट, कि मैं कोई भी आर वेक्टर लूं, आर स्टार, आर डॉट आर लूं या आर क्रॉस आर लूं, एंड देन आई कीप ऑन अप्लाइंग रोटेशन मैट्रिसेस एंड आई सी इफ दैट रिजल्ट रिमेन्स इनवेरिएंट और नॉट. If it remains invariant, it is going to give some interesting structure to the system. In fact, that happens. आपको पता भी है. But okay, I am not going to talk about it. However, I am saying that we do not read it from that point of view. हम लोगों का क्या होता था, जब भी हम लोग जो वेक्टर एनालिसिस आती थी तो हम वहां पे पढ़ते थे, oh, vectors they are unaffected by this rotation. Not the vectors themselves, but something else which is coming out of it. You know, the length of the vector remains invariant, right? By rotation around origin, correct?
Yes, sir.
Yes,
तो अब
sir.
आप सोचो, अगर आपको केवल आपको मैं ग्रुप थ्योरी देता तो आप उस तरीके से नहीं सोचते, आप इस तरीके से सोचते, अरे रोटेशन मैट्रिसेस तो एक ग्रुप बनाता है, अगर मैं इसे वेक्टर पे अप्लाई करूं तो कौन से कॉन्फ़िगरेशन पे अप्लाई करूं, आर क्रॉस आर और डॉट और कुछ अगर इनवेरिएंट रह जाता है तो दैट इज गोइंग टू गिव मी सम सिमेट्री ऑफ द सिस्टम. सो सिमेट्रीज आर एक्सप्लॉइटेड इन द ग्रुप स्ट्रक्चर व्हिच व्हेन अप्लाइड इन द ब्रांच ऑफ फिजिक्स or mathematics give you some beautiful constants of motion or the conserved quantities. आपको करने की जरूरत नहीं है अपना पूरा का पूरा डेरिवेशन, आप सीधे ग्रुप थ्योरी से ही वो रिजल्ट निकाल पाओगे. In fact, that is how the whole particle physics actually got involved. In fact, those of you who are going to take, particle physics or some of you might be in field theory, you will see that the symmetry properties are exploited very beautifully. Nuclear physics also exploits it very well. Since I told you Wheel and Wigner, these are the two proponents, and these two guys are nuclear and particle physicists. Okay, guys, we'll meet at 2 and then we will have further questions, but we will proceed from here. So do not think कि मेरी additional class में अब मैं केवल और केवल numericals पे stress डालने जा रहा हूँ. I will now make a flow. That means कि मैं जो करा रहा हूँ आपको वो follow को आप हर class में अब वो follow हो रहा है.
सर
जी
सर आपने जो कॉम्प्लेक्स का nth रूट ऑफ यूनिटी वाला बताया था,
yes.
सर उसमें मुझे आइडेंटिटी वाला समझ नहीं आया, क्योंकि आइडेंटिटी सर हम यूनिक रखना चाहते हैं.
श्योर नहीं, हम रखना नहीं चाहते, मैंडेटरी है ही. हाँ,
वो कंडीशन है सर. तो सर
हाँ.
जब हम जैसे हमारे पास 1 उसका सेट का एलिमेंट है,
हाँ,
तो सर उसके लिए 1 आइडेंटिटी है.
हाँ.
और सर जो -1 है, फिर उसके लिए अगर हम देखेंगे तो -1
वेट, इस पूरे ग्रुप का एक सिंगल आइडेंटिटी एलिमेंट होगा, राइट? इट्स लाइक एन एम्परर, इट्स अ सिंगल वन, देयर कैन नॉट बी मेनी. इनवर्सेस हर एलिमेंट का इंडिविजुअल होगा. किसी का इनवर्स हो सकता है खुद ही हो, किसी का इनवर्स कोई और हो, इनवर्स कुछ भी हो सकते हैं, पर एक एलिमेंट होगा जो इट इज अ सिंगल एलिमेंट व्हिच इज एन आइडेंटिटी एलिमेंट, सच दैट every element when multiplied with this element will leave that element unchanged, right? So identity element की तो ये प्रॉपर्टी है कि भैया वो किसी भी एलिमेंट से मल्टीप्लाई होगा, वो उस एलिमेंट को इनवेरिएंट छोड़ेगा, राइट?
यस सर, उसके लिए हम 1 यूज कर सकते हैं, क्योंकि 1 से हम
दैट इज
जब
द
भी हम
ओनली एलिमेंट, एक्चुअली देयर इज नो अदर एलिमेंट. यूज नहीं कर सकते. आइडेंटिटी एलिमेंट हैज टू बी यूनिक. It cannot be, there cannot be two identity elements in a system.
सर इनवर्स यूनिक नहीं होगा, मतलब इनवर्स
नहीं
चेंज हो
इनवर्स,
सकता
आप मुझे बताओ, अगर मैं -1 को i से मल्टीप्लाई करता हूं तो क्या मुझे i मिलता है?
नो सर,
नहीं मिलता ना।
माइनस है।
तो दो अलग अलग चीजों को लेट्स व्हाट इज हैपनिंग जनरली, इट हैपेंस व्हेनेवर यू आर स्टार्टिंग विद समथिंग, इट हैपेंस there exist two separate things. What are those separate things? One is identity, which is a single element of the group, जिससे कोई भी एलिमेंट मल्टीप्लाई करेंगे. सो आई शुड राइट फॉर ऑल gi's belonging to group. Yeah. And then there exists inverse, which is unique to an individual element. There is a possibility कि individual element खुद अपना ही inverse हो, but there can also be a possibility कि कोई और element इसका inverse हो, पर वो उसे होना पड़ेगा ग्रुप के अंदर. और हर एक ग्रुप एलिमेंट का एक इनवर्स होगा ही होगा उस ग्रुप में. अगर किसी भी एक एलिमेंट का इनवर्स नहीं हुआ, such that you are unable to get this identity inverse axiom fulfilled, तो इसका मतलब वो ग्रुप नहीं है. So inverses, for each of it there can be 3 separate inverses. There can be G1 one inverse to this G1, one inverse to G2, one inverse to G2. Once you find out that there exists a inverse, इनमें से केवल एक ही एलिमेंट उसका इनवर्स हो सकता है, दूसरा एलिमेंट कोई उसका इनवर्स नहीं हो सकता.
ओके सर.
So what basically we are saying, हाँ
सर आपने बोला था ना कि यूनिक होगा, तो सर आइडेंटिटी तो सर समझ आ गई थी कि यूनिक है.
मैं समझ गया, ये पूरे सेट के लिए यूनिक होगा और ये इंडिविजुअल एलिमेंट के लिए यूनिक होगा. मैं समझा. बट ओके, आई एक्चुअली वेंट लिटिल बिट फास्टर बिकॉज आई थॉट दैट वी जस्ट टुक केयर ऑफ एग्जैक्टली सेम चीज होगी. अगर आप वेक्टर स्पेसेस में जाना वापस देखना, मैंने आप लोगों को ये कराया हुआ है कि आइडेंटिटी यूनिक है और इनवर्स यूनिक है, बट द वे इट इज एग्जैक्टली द जैसे यहाँ पे है, आइडेंटिटी पूरे ग्रुप के लिए यूनिक है और इनवर्सेस हर एक एलिमेंट के लिए यूनिक है. या योर आपके क्वेश्चन की वैलिडिटी मैं समझ पा रहा हूँ. यू हैव अ वैलिड क्वेश्चन हियर. बट
सर मुझे
हाँ, क्या समझ में आया अब आप लोगों को? आई मीन ये वाली जो मैंने बात बोली.
यस सर.
Okay, good. Yeah, other question. Others can leave because I'm not going to teach till 2. Yeah, those who have questions they can ask.
सर मुझे कॉम्प्लेक्स इंटीग्रेशन से रिलेटेड एक क्वेश्चन पूछना था.
हाँ बोलो.
सर उसमें जब आपने हमें वो कराया था कि जब हम माइनस इन्फिनिटी से इन्फिनिटी इंटीग्रेट करते हैं, तो हमें जब हमें 0 टू इन्फिनिटी इंटीग्रेट करना होता है, तो हम ये देखते हैं कि वो फंक्शन इवन है या ऑड है, तब हम वो आइडेंटिटी यूज कर पाते हैं.
राइट.
तो सर अगर हमारे पास एक ऐसा फंक्शन है जिसकी हम पैरिटी आई मीन वो इवन है या ऑड है वो बता नहीं पाते, तो हम क्या मतलब प्रोसीजर यूज करेंगे सर?
देखो, आपके लिए पहली बात तो जो माइनस इन्फिनिटी टू इन्फिनिटी वाला पॉइंट है, अगर आपका वो नहीं लग रहा होगा, आपका कंटूर सी आई पुट एवरीथिंग अंडर सर्टेन कंटूर्स, राइट?
यस सर.
तो जो जितने कंटूर्स मैंने आपको दिए हैं, उन कंटूर्स के अंदर केवल और केवल एक ही केस में आप 0 से इन्फिनिटी कर पाते हैं, जबकि या तो वो इवन फंक्शन हो या तो ऑड फंक्शन हो. ऑड फंक्शन बहुत ही अच्छा है क्योंकि वो तो 0 रिजल्ट दे देता है, इट्स अ वेरी गुड वन. इवन फंक्शन होगा तो डेफिनेटली वो हाफ होगा, राइट? इट मे नॉट बी नेसेसरी दैट इट विल बी फ्रॉम 0 टू इन्फिनिटी. इट कुड बी, अगर मैंने मॉड ऑफ x माइनस a दे दिया है, तो हो सकता है वो माइनस इन्फिनिटी टू अप टू सर्टेन a एंड देन a टू इन्फिनिटी, ऐसा कुछ भी बन सकता है. But it will be symmetric about the mean. Sure?
Yes, sir.
Right. तो इसके बियॉन्ड आप किसी भी चीज को करेंगे तो आपके लिए क्वेश्चन को डिवाइड करना पड़ेगा उस मिक्स्ड इंटीग्रेंट को इवन एंड ऑड में, एंड देन ओनली यू विल बी एबल टू अटेम्प्ट दैट क्वेश्चन फर्दर. अगर आपको 0 से इन्फिनिटी करना है, माइनस इन्फिनिटी टू इन्फिनिटी में नहीं, पर अगर आपको 0 से इन्फिनिटी में करना होगा तो आपको किसी तरीके से इंटीग्रेंट को डिवाइड करना पड़ेगा इवन एंड ऑड में, and then only you will be able to solve that.
ओके सर. तो सर हमें उसे डीफॉर्म करना पड़ेगा जो क्वेश्चन हमें गिवन होगा.
हाँ, आपको क्वेश्चन में वो करना पड़ेगा, और अदरवाइज देयर आर सर्टेन बहुत ही लिमिटेड सेट ऑफ क्वेश्चंस, दीस आर वेरी स्पेसिफिक वंस, जहां पे कि आपको कंटूर्स ही चेंज करने की सोचनी पड़ती है, बट दोज आर वेरी वेरी रेयर वंस. वो मैं आपसे कहूंगा कि कॉम्प्लेक्स एनालिसिस में अगर आप आगे चलते जाएंगे तो रिसर्च तो उसमें भी होती है ना, तो कोई भी चीज ऐसा तो है नहीं कि रुक जाता है एमएससी के बाद. सारी चीजें एमएससी के बाद भी चलती रहती हैं. सो देयर आर ऑफ आई मीन केसेस, बट ओके, आई मीन लेट्स नॉट वरी अबाउट इट टू मच.
सर एक्चुअली हमारे ट्यूट में एक ऐसे क्वेश्चन था जो सर हमें समझ नहीं आया. उसमें हमें 0 टू इन्फिनिटी इंटीग्रल करना था, x अपॉन x क्यूब प्लस 1।
ओके,
तो सर अगर हम उसमें x को माइनस x करेंगे चेक करने के लिए कि इवन है या ऑड, तो सर x को तो हम माइनस x लिख सकते हैं, लेकिन जो डिनोमिनेटर था सर वहां पे हम पैरिटी नहीं बता पा रहे थे।
नहीं बता ही नहीं पाओगे, सही बात है। अगर
Yes.
आपने x ओवर x क्यूब प्लस 1 रखा हुआ है
तो सर मुझे वहां पे समझ नहीं आया था कि हम
बट
यहाँ
डिडंट
पे
यू
जो
डिस्कस इट विद द टीचर?
सर एक्चुअली उस दिन मैं क्लास में नहीं थी।
Okay, so try to ask it from the teacher first. I will let you ask it from the teacher or the students first. If not, then of course I will be able to tell you. But एक बार टीचर ने जब क्वेश्चंस दिए हैं ना, तो आपको ये जरूर कहूंगा कि आप पहले टीचर से डिस्कस कर लो, एंड देन आई एम देयर एनीवे। आप टीम्स पे मुझे क्वेश्चन लिख ही देते हो, मैं आपको सॉल्व बता तो देता ही हूँ कुछ ना कुछ हिंट,
यस सर, ओके
है ना।
सर।
एक बार आप करो, इट शुडंट बी दैट डिफिकल्ट। बाकी
you,
कोई
sir.
है? राइट, ओके, अदर्स, if any question is there?
Sir,
Yes.
Sir, the last question that you gave on the triangle, sir, I find it to be abelian group.
ये हम लोग कर लेंगे। मैंने कहा ना मेरा पॉइंट रिजर्व है। somebody asked me कि सर टेबल करके करेंगे कुछ चीज, तो when I reach to that point I will ask you to do it and you will yourself tell me कि आपका ये रिजल्ट क्या आया। फाइन, सो लेट्स जस्ट वेट फॉर दैट। आपको करना वैसे क्या होगा एबिलियन और नॉन एबिलियन के लिए, क्योंकि इट्स नॉट ए सिंपल थिंग। क्यों नहीं है सिंपल आपके लिए? आप देखो 6 एलिमेंट्स हैं, राइट? ई का तो 100% एबिलियन नेचर है, सो ई इंटू आर इज इक्वल टू आर इंटू ई, नॉट एन इशू। बट आपको सारे एलिमेंट्स का एक साथ चेक करना, आर डॉट आर स्क्वायर और आर टू डॉट आर थ्री, आर डॉट एल वन, आर डॉट एल टू, आर डॉट एल थ्री, देन आर स्क्वायर डॉट एल वन, आर स्क्वायर डॉट एल टू, आर स्क्वायर डॉट एल थ्री, और उसके बाद रिवर्स भी चेक करना है। तो ये छोटे नंबर्स, मतलब ये बहुत कम नहीं है ऑपरेशंस, देयर आर प्लेंटी एंड प्लेंटी ऑफ ऑपरेशंस। L1 into L2, I mean the simplest one is this. If you just do L1 into L2, will it be same as L2 into L1? अगर आप, I mean I will make this for everybody, क्योंकि अभी आप केवल कुछ ही लोग रह गए हो और आपने क्वेश्चन पूछ लिया, तो मैं आपसे ये जरूर कहूंगा L1 डॉट L2, दैट इज L2 अप्लाई करो पहले जो मेरे गिवन ट्राइंगल पे, एंड देन L1 अप्लाई करो, एंड देन रिवर्स द ऑर्डरिंग, L2 डॉट L1। आर यू गेटिंग द सेम रिजल्ट? एंड दैट विल टेल यू कि अगर एक भी पेयर एबिलियन नहीं है तो ग्रुप कैन नॉट बी एबिलियन। ग्रुप इज एबिलियन ओनली इफ ऑल पेयर ऑफ एलिमेंट्स आर commutative. Fine?
Okay, sir.
Yeah, I can understand that you might have done it with few of the rotations etc, and you will find that okay these elements are looking like abelian. ये ग्रुप भी थोड़ा इंटरेस्टिंग सा ग्रुप है, इसीलिए मैं ये ग्रुप को बेस्ड ग्रुप बनाता हूँ, बिकॉज यू मे बी एबल टू लर्न सो मेनी प्रॉपर्टीज आउट ऑफ दिस ग्रुप।
Okay, sir.
Good. Anybody else? Okay, if not, then I will stop recording.